Welcome back to the deep dive. Today we're looking at a material that has, well, it's sort of quietly become the real champion of practical 3D printing. I'm talking about PETG filament. We're going to move past the basic spec sheets and really dig into how it's evolved, from just another polymer to this go-to solution, some really diverse and frankly high-stakes applications.
Yeah, that's the key.
The sources you sent over were fascinating. They map out how this unique mix of strength, toughness, and its surprisingly easy printing has just launched it into some really unexpected places. So our mission today is to pull out the most practical, most surprising insights, the secrets, really, behind why this stuff is now being used for everything from your garden to, believe it or not, specialized surgical tools.
And if you take away just one thing today, it should be this: reliability and longevity. PETG steps into these roles where, your standard PLA would just completely fail.
It would just shatter.
No, it would shatter. Or where the hassle and fumes of ABS just make it impractical. It's that dependable workhorse. The part you print with it today is going to be just as good months, maybe even years down the line.
Okay, let's unpack that. Let's start with just the everyday stuff around the house.
Yeah.
This is where PETG really shines in functional parts because it can take a real beating.
Mm-hmm.
Unlike PLA, which is, it's great for a display model, but it shatters if you look at it wrong. PETG actually resists impacts. It bends before it breaks. It absorbs that energy.
It's all about that toughness. Exactly. So in a workshop, a garage, it's your ideal choice for anything that's under stress. Think tool holders, clamps, drawer organizers, custom mounts for things.
Right.
Or say you need to replace a little plastic part on an appliance, a lever or a cover, maybe a small gear.
Yeah.
PETG is the safe bet, as long as, it's not sitting right on top of a heating element.
I've made that mistake. I printed a heavy-duty shelf bracket in PLA once, and I came back 3 months later, and the whole thing had just sheared off. Too much weight, a little bit of temperature change, and it was gone.
And that's precisely why the pros rely on it. Here's a great little nugget for you. Many of the 3D printer companies themselves, big ones like Prusa Research, they actually use PETG to print the functional structural parts of their own printers.
Oh, wow. So they're literally building the machine out of the material it's going to use.
Exactly. If they trust it to hold their own machine together with all the vibration and heat, it's robust.
That's some serious confidence. It's also great for those little snap fit joints, right? The ones that need to flex just enough to click together but not break.
Perfect for it. It has to be flexible enough to snap into place, but strong enough not to break once it's there.
So that's inside. What about when you take it outdoors? Into the sun, the rain.
Now this is where it really, really wins against the other common filaments. Its single biggest advantage outside is its resistance to UV radiation and water.
And PLA just dissolves, basically.
Basically. If you've ever left a PLA print outside, like a garden marker or something, it gets chalky, it gets brittle, and the humidity just accelerates that whole process.
What about ABS? That's supposed to be stronger.
It is stronger, but UV still gets to it. Over time, it becomes really brittle. PET, on the other hand, it just holds on to its mechanical properties and its looks for way, way longer.
So we're talking about things that actually live outside long term.
Absolutely. We're seeing it used for durable flower pots, protective cases for outdoor security cameras or sensors, even parts for drones and RC planes where you need it to survive a, let's say, less than perfect landing.
The inevitable crash.
The inevitable crash. If it has to face the elements, PEG is just the smarter choice.
Okay, let's shift gears now from that rugged outdoor strength to something much more delicate. I'm talking about optical clarity. PEG has this amazing ability to print clear things, but anyone who's tried it knows how hard it is to get it actually clear. It usually just ends up looking cloudy.
That fogginess, that's all about light scattering. Every time light crosses from one layer to the next, it bends. And because there are these microscopic air gaps between the lines of plastic, the light just gets scattered all over the place.
It's like looking through frosted glass.
Exactly.
Yeah.
So if you want true transparency, the mission is to basically weld those layers together to make them one seamless piece of plastic.
And this is where it gets counterintuitive, right? Because my first instinct for a good-looking print is always, moderate heat, lots of fan cooling to keep the details sharp.
And for transparency, you do the exact opposite.
Yeah.
You basically throw that conventional wisdom out the window. The goal is maximum fusion, zero air gaps.
Okay, so what's the first big change?
Temperature. You have to print hot, really hot, right at the upper limit for PETG, so you're pushing maybe 250, 255 degrees Celsius. That heat is what melts the layers into each other.
And I'm guessing you don't want to print fast either.
Absolutely not. You have to print slow, very slow, like 20 to 30 millimeters a second. It gives the material time to lay down evenly and just sort of settle in.
Okay, hot and slow. I get that. But the part that really messes with my head is layer height. To get a smooth, clear surface, I think you want the thinnest layers possible, like 0.1 millimeters.
And that's the critical mistake everyone makes. Thinner layers mean more layers. More layers mean more boundaries for the light to hit and scatter.
Ah, okay. So fewer boundaries is better.
Precisely. You want the thickest layer height you can get away with. For a standard 0.4 millimeter nozzle, you use something like a 0.3 millimeter layer height. Fewer layers means less scattering.
You're trading that vertical resolution for optical clarity. Got it. What about the width of the line itself?
Same logic. You want those lines to squish together side by side, so you increase the extrusion width maybe to 120, even 150% of your nozzle diameter. It forces the plastic to spread out and fill every little gap.
And the final piece of the puzzle.
Turn the cooling fan off. Completely off. You want that heat to linger as long as possible to help everything fuse into one solid, clear piece.
So high heat, slow speed, thick lines, and zero cooling. That's the recipe, whether you're making a solid clear block or a vase in spiral mode. Let's move on to the most specialized area we have, which is medicine. This is a field where, the slightest error is just not an option. And this is where PETG is proving itself over the standard hobby stuff.
It really is a professional tool here. So for non-sterile uses, its stability and strength are just invaluable. Surgeons are now regularly printing one-to-one scale anatomical models from patient CT or MRI scans.
Models of what? Bones? Organ?
Both. Bones, organs, even tumor sites. It allows them to plan a really complex surgery, to practice making cuts, to figure out the best approach, all before the patient is even on the table. And that can drastically reduce time in the operating room.
But that's still just a planning tool, right? A prop.
Yeah.
What does it take to get that print into the operating room to be used during the surgery as, say, a custom drill guide?
Sterilization. That's the hurdle. It has to be perfectly sterile. And the standard method in any hospital is the autoclave. It uses high-pressure steam at around 121 or even 134 degrees Celsius.
And I'm guessing PETG does not like that kind of heat.
Not at all. That's well above its class transition temperature. An autoclave will turn a precise PETG part into a warped, useless blob of plastic.
Yep.
It would be completely unusable.
Doesn't that make it a non-starter? If you can't sterilize it properly, how can you ever use it for real surgical tools?
That is the crucial question.
Mm-hmm.
And the solution, fascinatingly, already exists in hospitals for other heat-sensitive equipment. It turns out PETG is compatible with specialized low-temperature methods.
Okay.
Specifically, the sources point to something called hydrogen peroxide plasma sterilization, or HPO.
HPO plasma, and that runs a lot cooler.
Much cooler. It operates at a maximum of about 55 degrees Celsius. And studies show that when PETG parts go through HPO sterilization, the deformation is absolutely minimal. It's clinically negligible. The parts hold their shape perfectly.
So that's the key. That compatibility is what elevates it from a model on a desk to a tool in a surgeon's hand.
It's the unlock. It means hospitals can 3D print a low-cost, patient-specific surgical guide, sterilize it safely with a protocol they already have, and then use it with confidence in the operating room. It's a huge leap.
To bring this all together then, let's talk about the final piece of the puzzle for anyone considering it.
What?
Cost.
Right, the bottom line.
Price obviously changes everywhere, so let's talk about it relatively. Where does PETG sit compared to the other big names, PLA and ABS?
It's generally a mid-range material. It's usually a little bit more expensive than your basic budget PLA, maybe 15 to 30% more. But it's often about the same price, or sometimes even a little cheaper than a good quality ABS.
So if a standard roll of PLA is, say, $20, PETG is what, 25, 30?
That's a good ballpark, yeah. Around that $25 to $35 range for a standard, good quality spool. What's really interesting, though, is how the market is segmenting. You can now get RPTG, which is recycled.
And that's cheaper.
Often, yes. It can sometimes even be cheaper than standard PLA, dipping below that $20 mark. It makes it a really compelling budget option.
And then on the other end, you have the high-performance stuff.
Exactly. You have high-speed PETG, which is designed for the new super-fast printers, and that sits in that mid-range. But then you get into engineering-grade materials like PPG-CF, that's PETG reinforced with carbon fiber.
And the price there must jump.
It jumps a lot. You could be looking at double or triple the price, easily $50 to $80 a spool, or even more. But you're getting a massive increase in stiffness and performance for that.
So it's not just one material. It's really a whole family of materials for different jobs, from cheap outdoor signs to critical engineering parts.
And that really gets back to its core value. PTG bridges that gap. It gives you the ease of printing you get from PLA, but with the strength and weather resistance that used to mean you had to struggle with something difficult, like ABS. And now we know it even has this path into specialized professional use through things like HPO sterilization.
So after this deep dive, what's the final thought for you, the listener, and your next project? Well, think about this. Given how much better PETG holds up outdoors than PLA and its superior UV resistance to ABS, consider the hidden cost of choosing the wrong material. Think about how many times you've had to reprint a part because the PLA failed in the sun or shattered on impact. PETG can stop that replacement cycle. So ask yourself, what bracket, what tool handle, what little gadget in your home could you print in PETG today that would otherwise just fail on you next season? That's the real efficiency this material offers.